Today we are going to study the block diagram of pulsed radar system. Before going to the block diagram, let's first consider the basic working of pulsed radar system. In pulsed radar, a pulse waveform, generally a train of narrow rectangular shaped pulses modulating a sine wave carrier, is transmitted as shown in this figure, and the range or distance to the target is determined by measuring the time t taken by the pulse to travel to the target and return to the radar station. Then, since electromagnetic waves travel with the velocity of light c, the range r for stationary target is given by 2r is equal to c into t, where this factor 2 is to account for two-way propagation. And from that we can write r is equal to ct by 2, where 2r is the total distance between the radar and the target, t is the time taken by the electromagnetic waves to cover the distance 2r, and c is the velocity of light. Let's now consider the block diagram for the pulsed radar system. As we said earlier, in pulsed radar system, a pulse waveform is transmitted. So when we consider this block diagram, it has the provision to generate the pulse waveform. By using the trigger source, pulse modulator and output tube, this pulse waveform is given to the duplexer side. Then duplexer will forward that to antenna, and from that it is transmitted. Then when it hit on the target, a portion of that signal gets reflected back, and that is received by using the receiver antenna and is directed to the duplexer, and from the duplexer that signal is directed to the receiver section. Then at the receiver side, after proper operations, the information about the target is displayed on the radar display. Let's now consider the functions of each block in detail. First, consider the trigger source. This trigger source provides pulses for the modulator. Then consider the pulse modulator. This pulse modulator provides rectangular voltage pulses which act as the supply voltage to the output tube, thus switching it on and off as required. Next, consider the output tube. The output tube may be an oscillator tube such as a magnetron oscillator, or an amplifier such as klystron, traveling wave tube, or crossed field amplifier. Then if an amplifier is used, a source of microwave is also required. Low power radars use IMPAT or gun oscillators or TRUPAT amplifiers. Below C-band power transistor amplifiers or oscillators may also be used. The pulse modulated sine wave carrier then travels via a duplexer to the antenna, where it is radiated into space. A single antenna is generally used for both transmission and reception. Usually, parabolic reflectors with center feed arrangement is made use of. Let's now consider the function of duplexer section. The receiver must be protected from damages caused by high power of the transmitter, and this is the main function of the duplexer. The duplexer also serves to channelize the returned echo signal to the receiver and not to the transmitter. The duplexer consists of gas discharge tubes, one known as TR, the transmitter receiver tube, and the other as ATR, anti-transmitter receiver tube. The TR tube protects the receiver during transmission, and the ATR helps in directing the received echo signal to the receiver. Let's now consider the receiver section. The receiver section is usually of super heterodyne type, whose function is to detect the desired echo signals in the presence of noise, interference and clutter. Then the receiver in pulsed radar consists of the RF amplifier, mixer local oscillator, IF amplifier, detector, video amplifier and radar display. The first stage of the receiver is low noise amplifier. It is a low noise transmitter amplifier or a parametric amplifier or a traveling wave tube amplifier. Silicon bipolar transistor is used at lower radar frequencies, that is from 1215 to 1400 MHz, and the gallium arsenide FET is preferred at higher frequencies, and it raises the strength of the echo signal. After the low noise RF amplifier, the next section is mixer and local oscillator section. This mixer and local oscillator section converts the RF signal output from the RF amplifier to comparatively lower frequency levels called intermediate frequency. Thus, in a mixer stage, the carrier frequency is reduced. Then after converting the RF frequency to intermediate frequency by using this mixer and local oscillator arrangement, the next section is intermediate frequency amplifier. This intermediate frequency amplifier consists of a cascade of tuned amplifiers and provides the main receiver gain. Then it should be designed as a matched filter to get maximum peak signal to mean noise power ratio at the output. A typical IF amplifier for an air surveillance radar must have a center frequency of 30 MHz or 60 MHz and a bandwidth of 1 MHz. Then the next stage is the detector stage. This detector is often a Schottky barrier diode which extracts the pulse modulation from the IF amplifier output. The detector output is then amplified by the video amplifier to a level where it can be properly displayed, usually on CRT directly or via computer processing and enhancing. The synchronizing pulses are applied by the trigger source to the display device or the display indicator.